Hi class, this video is for Hotelling's t-square, which is essentially a multivariate t-test. It's actually not that popular, and it's for the same reason that people just prefer doing ANOVA to t-test. It just sounds fancier. Um, Even though they only have two groups, they'll run ANOVA, and the software is calculating a t-test, but they said they ran an ANOVA. So it's the same with the hotellings. A lot of people will do a MANOVA, but they will only have two groups. And really what they're doing is hotelling's t-square. So let's start learning about it. So why have more than one dependent variable, and why use multivariate statistics rather than univariate? After all, we already learned univariate statistics. So for me, I think the most important reason for having multiple dependent variables is just because it's more realistic to what data looks like in real life. You're probably going to have multiple measures that have an impact, that have an effect on what the outcome variable in your study is going to be, and you want to model that as realistically as you can possibly do it. Why using multivariate statistics rather than univariate? Well, the first reason that you should always keep in mind is if you do multiple t-tests or multiple ANOVAs as opposed to using the multivariate approach, you're going to inflate your type 1 error. Let's say that I conduct 2 or 3 t-tests. So every time that, for every t-test that I conduct, I have an alpha of 0.05, so that's going to increase it to 15. So I'm increasing the type 1 error, and it's more likely that whatever I found in my study, I could commit a type 1 error. And even though I did all that work, I'm ruining it by using the incorrect statistical procedure. Um, I think another good reason to use multivariate statistics is to have the correlation that you would usually have between the dependent variables. And again, if you do an independent ANOVA for each, as opposed to doing a MANOVA, let's say, you're ignoring that relationship between the dependent variables, and you don't want to do that. It's not realistic. It would be more realistic to model the correlation and the relationship between the dependent variables in your analysis. And in real life, you're going to have a good theoretical reason of why those variables are together and why there's a correlation between them. So here I have an example for the GRE. Like, there's a reason why you would have all of those three as dependent variables. I mean, they're from the same test, they were taken at the same time. Even though they're essentially different and they might be assessing different things, there's a relationship between them. So before we go into Hotelling's t-square, let's review the type of test. I'm sorry, the type of t-test that there exists. So there's actually 3 of them: single sample, independent samples, and dependent samples. And dependent sample has a lot of different names. I've seen related samples, pair samples, match pairs or match samples. I've seen also repeated measures, and I'm sure there's another one that I'm forgetting. The simplest one is the single sample, and I've seen it. It's often overlooked. I personally don't always cover it. And it's just comparing whatever value you have in your sample, whatever mean value you have in your sample, to a population value. So I get the mean from my sample, and then I compare it to whatever's in the population. And the population value can be something you get from the literature. It could definitely be a different population. I don't know, people in a different country compared to those in the US, the population mean in the US. That would be reasonable. Or it could be something from historically, that was what the value was compared to. It varies. The pair hypothesis is essentially just comparing the mean to a value. And then for the alternative, you would have different, greater than, or less than. It really depends on the research question. So for example, let's say that I want to compare the weight of cats. I don't know. And I think it's always good. The population weight mean of cats would be 3 kilograms. So that's what my null is saying. And I want to see if it's greater for my sample, or I think it's greater for my sample. The code would look like this. I would just have t-test. Here I have the data frame with, it's essentially a vector with the data from my sample. Then I tell it what the population value is going to be. And then I tell it what hypothesis I wanted to test. In this case, I had greater than, so I went with greater. So let's go into independent samples. I think the most popular design for independent samples is gender, where you would have females in one group, males in one group, and then you would compare their averages. The research questions for this is basically, is there a difference between the two samples? And what we're really comparing is the mean. The pair of hypotheses, you would have the null, where you're saying that they're equal, there's no difference between the groups, and then this should be alternative. And then the alternative is saying that there is a difference. And you can have just the difference, you don't know the direction, or greater or less than, depending on the research question. So I use the data set sleep for this next example. And we're not actually going to be doing t-test, so you don't really have to do this one if you don't want to. But this data set has 20 observations and 3 variables in this 3 columns. It's essentially they're comparing 2 different drugs to make people sleep longer. So extra is the numeric increase in hours of sleep. Group is which group they belong to, which drug they gave to the people, and then ID is just, the participant ID. The research question would be, is there a different number of hours between the 2 drugs? If you work for a pharmaceutical company, you probably want the one that makes people sleep longer. So I use the same function, t-test. Here I'm going to have the dependent variable, which is the number of hours of sleep, and then I give it the independent variable, which is the group they belong to. I tell it what data set to get the data from. Bar.equal equals true is just telling R to use the regular t-test as opposed to a non-parametric option. And then this is what the output looks like. It gives you the confidence interval. That's what it would look like. And then it gives you the t statistic over here. Okay. And then degrees of freedom, and that looks right because it was 20 people, 1 minus for each group, and then your p-value. And at least it's not a scientific notation, so that's okay. I'll try to highlight this by the time I give you the notes. Cool. Now let's talk about the pair samples t-test. So I think the most popular design for this one is definitely before and after. Like we do some kind of intervention and then we measure them again on the same variable, and we hope that there's a difference. I don't have a data set for this one, but just imagine that you are using that sleep data set and that you measure them at one time and then you measure them at a second time. You would have your dependent variable here. You would have time here instead of group. You would tell it the data set here, and then you would say pair equals true, so it knows that it's using the pair t-test formula. So it's the same for format for them. You just have to add the pair equals true. It doesn't even recognize the difference between time and group. That's why you have to tell it this is paired. Here I have the pair hypothesis. It would be the difference is equal to 0. That means that there's no difference between the groups at the 2 time points that you measure them. And then here that there is a difference. Either you don't know the direction and you're testing for difference, or greater or less than. It depends on the research question. You can think of hotellings as multivariate t-tests. So here I have the way you calculate the test statistics, the test statistic for a t-test, normal single sample or actually 2 sample t-test. You subtract the 2 sample means essentially, You divide by the variance pool and you multiply by a correction factor, essentially. The variance pool is useful for social scientists because sometimes they have different sample sizes in their two groups. I have been in departments where you're not at the mercy of participants, not at the mercy of like humans for your data. So you actually don't have to use the variance pool because the sample sizes are the same. Um, so it's useful. Um, and what's going to change for our for hoteling is that these two are essentially going to become vectors. So remember a pair of hypotheses was just mu equals either a number for the single sample or the second sample if it was independent, or the second time, I'm sorry, or comparing to a difference if you were doing paired. So for hotellings, our null hypothesis would be um, comparing the first vector to the second vector, and it's essentially um, the two dependent variables that we have here. And this would be how we calculate them. And you know that this little piece represents the variance covariance. These are capitalized and have a little bar on top of them, and that represents a vector as well. And this is a simplified form of the variance pool. Don't ask me how to arrive to that. I've forgotten. And we're not going to calculate this by hand. Another thing you need to remember, or maybe you don't know, is that F statistics are essentially T statistics square. So, and I only mention this because you might decide to do your hotellings in a different software someday. I know that when I was preparing the material for this lecture, I was using an example from SAS, and it actually gave me the F, the output as an F, and R gives me the T. So that's just always something that you have to check. Are you being given the F, the T squared, or are you being given T that you have to square it to get the F? Here, so one thing that set your text, like we use F tables to find significance. Nobody uses tables anymore. R is going to give us a p-value. And that's, I guess, one of the flexibility of using R. Like you can always find a package that's going to give you a p-value. I have worked with other software like Stata, and they'll give you the test and they'll give you the value that you look for on the table. But it's just easier to look at the p-value. Like you're saving yourself 3 seconds, and that's nice. Here I have how to calculate the degrees of freedom for that. The first degrees of freedom is going to be the number of dependent variables. And the second degrees of freedom is the two sample sizes added minus the number of dependent variables minus 1. Now let's talk about the assumptions. So the data are sampled from a population. We need to check the assumption of variance covariance, and we're going to use box M test. You can use Levine's, you can use Bartlett's. I tend to use box M test. You need to know that your values are independent, and remember, this is not something that we can check numerically. There's no test for this. You can definitely look at the residuals for sure, or it's something that comes from the design for the most part. And we're going to check multivariate normality using Shapiro-Wilk. Cool. Things to know, hoteling t-square is robust to violations of multivariate normality. And you have to think about it this way. This is also true of t-tests. They are essentially tests that were created for small sample size. Robustness means that this test, even though there's errors in it, the test will complete itself, basically. In this case, you are anticipated to have deviations for normality due to small sample size, but hotelling's t-square will still run. So that's always nice. It is sensitive to violations of variance covariance, and it's also true of t-test. And it has more to do with if you have a very large discrepancy in your sample sizes, it's also very likely you're going to have differences in the variance in the samples. And there's no, you might be able to run a non-parametric type of test for t-test. You might be able to do some kind of logistic regression if the multivariate t-test doesn't work. But other than that, I don't know how else you would fix that. Okay. Now let's start with our first example for hotellings. Cool. We're going to do a single sample hotellings t squared. We're going to use data from 1985 from the USDA, which commissioned a study on women's nutrition. They sampled 737 women for 5 nutritional components: calcium, iron, protein, vitamin A, and C. Not sure why this one's, I'm not a nutritionist. We're going to use the data set nutrient.txt. It has 6 variables. I think it has the ID and then the 5 uh, nutritional components that we're interested in. So whenever I give you a text file, make sure you use the from text space or it's not going to import correctly. So essentially, we're doing a single sample. So this is the recommended population value that the USDA wants, and we're going to compare it to our sample, and they look different, but we want to see if they're statistically different. The research question is: are the women in our sample meeting the federal nutritional guidelines? And if they are failing, we want to know in which one they're failing. We could take a different approach. We could do a t-test for each one of these, like a single sample t-test for each one of this. The problem is whenever we do multiple t-tests, we could inflate the type 1 error. For example, think about it this way. If I do a t-test for this one, that could be, if I'm using a 0.05 alpha, that's 5%. 5% of the time I could be incorrect and committing type 1 error. Another 5% for iron, another 5% for protein, another 5% for A, and another 5% for C. So that's a lot. Once you add them, it's a lot. So what's recommended in this case is that when you do multiple t-tests, and this happens a lot in my experience, what you should do is call a Bonferroni correction. So a Bonferroni correction consists of basically taking the alpha, which usually it's 0.05, and then dividing by the number of tests. So for me, it would have been 0.05 over 5, and that would leave me with an alpha of 0.01. And then that 0.01 would be what I use to interpret my results. So it doesn't matter what I get from my t-test, now I have to compare it to 0.01, which makes it harder to reject. It's a more conservative test, essentially. And you can read more about it in this page in the Navarre and Foxcroft textbook if you want to. I like my equation better. I think they have a more complicated equation, but I feel like the content of the section would still help you. Remember, this is a single sample, so our null hypothesis would be mu equals whatever the population value is. And here it will be essentially 1,000 for calcium, 15 for iron, and so on. Okay, data screening, yay! So if you import your data, the first thing we have to do is give it names because it doesn't have them. So I just use the names function. And then the first variable is ID, the second one calcium, and so on. And then I did summary to look at the data. It was conveniently doesn't have any missing data. I was happy with that. And this is exactly what the text of the problem said that it had, like 737 and 6 variables. I checked for missing. I already know there's nothing missing. I'm happy as a clam. I'm going to check for outliers using Mahalanov's distance. Notice here in nutrient how I'm using only columns 2 to 6. The reason I'm doing columns 2 to 6 is because the first column is ID and I just don't need it for anything. Could have I just removed that column before I even started this? I could have. It would have probably been easier. Um, so here's where I get my cutoff to compare my Mahalanobis outliers to. Um, nice, I call it cutoff. Then I use the Mahalanobis function, nutrient, only the columns that actually have data, yada, yada, yada. I use summary to compare each of the values that Mahalanobis distance found to the cutoff that I selected, and it found 16 outliers. So I'm going to remove those 16 outliers and I'm going to save everything into a new data set that I usually call no out. Then I check for the dimension of that data set, and this is what I have left. Nice. So on using Mahalanobis distance as a criterion, we ended up with 721 observations. Let's move into assumptions now. We're going to check normality. We're going to use the library MB norm test, which I think we used before. I do have to transpose the data, and again, I just ignored the first column, which is the ID column. And then I did the M Shapiro test function. Gave me the W, and it gave me the p-value, which is in scientific notation, but we know it's very small. The assumption of normality was checked using Shapiro-Wilk. We reject the null hypothesis, so that means that we are not meeting that assumption. And then I added here a citation for the package. What can we say when we don't make this assumption? We can always say that the data is small, and that's normal. And we can always trust in the central limit theorem. Nice. I'm going to check for correlations. I'm going to use the GG Gallery library. And then I'm going to do correlations between the 5 nutrients. They don't look that highly correlated, calcium and vitamin C. Again, I'm not a nutritionist, so I don't really know what the maximum would be here or what would be very bad. I think this requires a little bit of content area expertise. But those are the correlations. They are weakly correlated in my opinion. This one has a really nice linear pattern. I like that. At least none of the correlations are 0, so we can definitely use them as multiple dependent variables for our Hoteling's t-test. Hoteling's t-square, I'm sorry. To actually run my analysis, I am going to use the library ICSNP. I'm sure it stands for something. Then I have to create a vector. So this vector is actually that table that we had at the beginning. I'll edit this out, this table. It just has the population values that we want to compare it against to. Then I actually use the Hoteling's function. I tell it what my data set is, the variables that I'm going to be using, and then I tell it what the population values are going to be. I could have just left this as 0 for all of them if I just wanted to compare it to 0. In this case, we actually had values to compare it to that the government was giving us. So here we go. Our output, this is the t-square that you're going to report. Your 2 degrees of freedom, and then your p-value. And again, annoyingly, the p-value is in scientific notation, but that just tells you that it's a very small p-value. So after the data were screened for multivariate outliers, we ended up with this sample size. We checked the assumption of normality, which was not met. However, we trust in the central limit theorem. Then we perform Hoteling's T and the ICSNP package. I give the citation there. Concluding that the women were not meeting the recommended standards. So remember, the null hypothesis is saying that whatever we have in our sample is the same as what we have in the population, which are those recommendations from the government. We rejected the null hypothesis from this p-value. So yeah, they're not meeting those standards. Then we can go back to the table. We're going to use data from 1985 from the USDA, which commissioned a study on women's nutrition. They sampled 737 women for 5 nutritional components: calcium, iron, protein, vitamin A, and C. Not sure why this one's, I'm not a nutritionist. We're going to use the data set in nutrient.txt. It has 6 variables. I think it has the ID and then the 5 uh, nutritional components that we're interested in. So whenever I give you a text file, make sure you use the from text space or it's not gonna import correctly. So essentially we're doing a single sample. So this is the recommended population value that the USDA wants, and we're going to compare it to our sample, and they look different, but we want to see if they're statistically different. The research question is: are the women in our sample meeting the federal nutritional guidelines? And if they are failing, we want to know in which one they're failing. We could take a different approach. We could do a t-test for each one of these, like a single sample t-test for each one of this. The problem is whenever we do multiple t-tests, we could inflate the type 1 error. For example, think about it this way. If I do a t-test for this one, that could be, if I'm using a 0.05 alpha, that's 5%. 5% of the time I could be incorrect and committing type 1 error. Another 5% for iron, another 5% for protein, another 5% for A, and another 5% for C. So that's a lot. Once you add them, it's a lot. So what's recommended in this case is that when you do multiple t-tests, and this happens a lot in my experience, what you should do is call a Bonferroni correction. So a Bonferroni correction consists of basically taking the alpha, which usually it's 0.05, and then dividing by the number of tests. So for me, it would have been 0.05 over 5, and that would leave me with an alpha of 0.01. And then that 0.01 would be what I use to interpret my results. So it doesn't matter what I get from my t-test, now I have to compare it to 0.01, which makes it harder to reject. It's a more conservative test, essentially. And you can read more about it in this page in the Navarre and Foxcroft textbook if you want to. I like my equation better. I think they have a more complicated equation, but I feel like the content of the section would still help you. Remember, this is a single sample, so our null hypothesis would be mu equals whatever the population value is. And here it will be essentially 1,000 for calcium, 15 for iron, and so on. Okay, data screening, yay! So if you import your data, the first thing we have to do is give it names because it doesn't have them. So I just use the names function. And then the first variable is ID, the second one calcium, and so on. And then I did summary to look at the data. It was conveniently doesn't have any missing data. I was happy with that. And this is exactly what the text of the problem said that it had, like 737 and 6 variables. I checked for missing. I already know there's nothing missing. I'm happy as a clam. I'm going to check for outliers. Using Mahalanov's distance. Notice here in Neutron how I'm using only columns 2 to 6. The reason I'm doing columns 2 to 6 is because the first column is ID, and I just don't need it for anything. Could have I just removed that column before I even started this? I could have. It would have probably been easier. So here's where I get my cutoff to compare my Mahalanobis outliers too. Um, nice, I call it cutoff. Then I use the Mahalanobis function, nutrient, only the columns that actually have data, yada yada yada. I use summary to compare each of the values that Mahalanobis distance found to the cutoff that I selected, and it found 16 outliers. So I'm going to remove those 16 outliers, and I'm going to save everything into a new data set that I usually call no out. Then I check for the dimension of that data set, and this is what I have left. Nice. So on using Mahalanobis distance as a criterion, we ended up with 721 observations. I went ahead and added the labels for so that you know which type of counselor you have in this graph. Remember that for box plot, this line usually represents the median. So for counseling effectiveness, I know that the median for Roger is 2, and I know that the median for Adler is 5. How do I know that? Let me scroll up. Here it is. So median 2, 5, median 3, and 8. Let me scroll down now. Yeah, between 2 and 4, and definitely 8. That's how I knew which one was which. I'm going to check the assumption of normality. I did the same thing we did before, same library. I transpose the data. I don't have to eliminate any columns here because I input it manually, and I already removed everything that I didn't need. I went ahead and did Shapiro walk. I do not reject normality. Isn't that nice? Then I went ahead and checked for box M test. I use the library heaplots. I really like this library, by the way. I went ahead and column bind the data set, the Y12, with the group variable. Remember, this is the one that tells us in what group they are, 1, 1, 1, 2, 2, 2. So I did that so that I could actually tell box M test what the groups were. So here I tell it, from this new data set that I created, I want you to do box M test on columns 1 and 2, and then by the groups 1 and 2 that are in column 3. That's what we're doing here. And then I have this output. Here's my chi-square test, my degrees of freedom, and my p-value. So remember, the null hypothesis is that the variances are equal, and I don't reject it, so I'm happy as a clam. That's what I wanted. Data analysis. So we're going to use this library that we've used before. Here I went ahead and did the Arbine again I actually didn't have to do it. You can remove that piece of code if you want to. Then I went ahead and did hotellings. I put the 2 variables that have the ratings of satisfaction and effectiveness here as the dependent variable, and then I gave the variable that has the groups for the 2 types of counselors. This is my output. Here's my t-square, my degrees of freedom, my p-value. I reject the null hypothesis, so there is a difference between the 2 types of counselors. Interesting. In the ratings of satisfaction and effectiveness. So just a little summary of what we did. We went ahead and calculated the correlations between the 2 dependent variables. They were pretty high. I went ahead and did 2 box plots for seeing the differences, and from those box plots we could see that the Adler counselors had higher ratings. So just from looking at the data graphically, we knew that we were going to find significance. We also tested for normality, and we tested for variance covariance. And then we went ahead and did the hotellings t-test. So let's talk about power analysis. We're going to be using G-power again. There's several factors that are going to affect the power of the test. The type 1 error rate, or the alpha level, if you want to think about it that way. The sample size. the effect size. If I give you a very large effect size, you probably will need less people to find significance, basically. If I give you a very small effect size, you're probably going to need more people to find what it is you're looking for in that sample. You need the standard deviation, and you need the directionality of the hypothesis. So in general, two-tailed tests are harder to reject, to find significance, than one-tailed test. And that's just because it splits the data into two tails, making it smaller, so it's more difficult to have a statistic that falls into that smaller area. Those are things that can affect your power. You can do power analysis in R. There's a package for it called PWR. I personally have not used it. I have this link if you want to play with it. I've just been using GPower for a long time, so and nobody has charged me for it, so I keep using it. So we're going to need GPower. For Hotelling's T's, we're going to use the F test. It's going to be under F test, and then we're going to select Hotelling's T 2 group because we have the two types of counselor. We're going to go with a priori. We're going to use a large effect size. I think I use 1.5, alpha of 0.05, power of 0.80. That's what we use usually for this. Allocation, so if you have equal sample sizes, you can use 1 here. I'm pretty sure we don't have equal sample sizes, so I use 0.5. And we had two dependent variables, two response variables, which is effectiveness and satisfaction. So I went ahead and did my power analysis to achieve a power of 0.81. It's recommending me that I have a sample of 15 in one group and a sample of 8 in the other group. And this is how you would write it up. Remember to cite GPower. GPower actually has an asterisk here, but because of the way I create my notes, I can never put it in. But that's not an issue that you might have. And then you can go to your textbook on page 54. It has a whole write-up on how to present your results for Hotelling's t-square. So now we're going to do Hotelling's, and we're going to compare the mean differences for two groups. So emphasis on difference, because that's essentially what we're doing. The two groups are going to be 5th grade boys and girls. So there's two ways you could approach this. You could test for the pre and the post, or you could test for the difference between boys and girls. Would it be easier to do like a 2x2 ANOVA? Yeah, it probably might be. Or in this case, if you want to account for the multivariate aspect of the measures, you can definitely do a ANOVA. But we're just practicing Hotelling right now. So that's our data. We have pre and post scores for pop quizzes, and we have scores for boys and girls. So the research question is there a difference overall in the mean differences, emphasis on that, of pop quiz scores for boys and girls? We use the same libraries that we've used for our previous Hotelling examples. Then I created vectors, pre-boy, post-boy, pre-girl, post-girl. And then I created a new data frame, and I call it my data. I went ahead and used the attach function so that when I call pre-boy, R knows immediately where to find that variable. This is what my new data frame will look like. I have 5 observations in each of the variables. It's not a whole lot. I went ahead and computed a summary to find the mean. And then I realized that one of the biggest disadvantages of summary is that it doesn't provide the standard deviation, and you definitely need that for reporting purposes. The way I get the standard deviation is that I use the SD function, and then in parentheses just put the variable that I want to use. You can also do mean parentheses pre-boy, and it's going to give you the mean if you don't want to do summary. And I think that's what your textbook does. Now I want to pause here where it says difference in scores. So what I did was that I subtracted post boy minus pre boy, and I did the same for girls, and I stored that in variables called diff boy and diff girl. I know that this looks really weird, but if you recall from your undergrad stats when you were doing parity tests, um, this is what the hypothesis would look like the mu difference, and then you compare it to a null, to a zero. And then the alternative would be greater, less, or different, or whatever you were interested in. But you also have to find the difference between the two time points. You would find the mean of the differences. You would find the standard deviation of the differences. It's a very long problem to do by hand, even when it's in the univariate case. So that's what I'm doing here. And then I went ahead and did the means, and I'm gonna highlight this because we need. So the mean for diff boy is 0.05, and for girls is 3.4. That's the mean difference. That's the mean difference for girls. This is what my new data set looked like. So what I did is I created a new data frame, and I call it ydiff, and I put the differences inside of that data frame. It was mostly to create this graph. So my y has the mean differences. Here I have the groups. This is my x label. Notice how both of them are crossing that zero. That kind of tells you that you're not going to find significance. You don't have to remember that. What I personally like on this graph is I can see that the girls have a lot more variability already. So that's one thing. So let's go ahead and do our data analysis, which is going to take us like 2 lines of code. It's going to be done pretty quickly. I just need to give it a 0 to what the null hypothesis is going to be. For mu null, what that's going to be. I could have just put a 0 here. That would have been okay. And then I'm going to do a hotellings for the difference in the boys, and then I'm going to do a hotellings for the difference in the girls. This is the output for the boys. No significant differences. And the output for the girls. Even though there's a lot more variability, there's no significant differences there. And here I have the write-up, and I gave the page number if you want to look at how Schumacher describes it. So things to remember, I just compare the differences in the scores for girls to a null, and then the differences in the scores for boys to a null. Your textbook has a second approach where you could just look at, I did approach 1, where you could just compare the pre and the post if there was difference across time. It's honestly the same process. Like you're just gonna have pre-post, you're gonna create a variable for groups, and then you're gonna find the differences, and then you do the same thing that we've done before. So you're welcome to look in your textbook for that type of example. And I think that's it for this, for this lecture.